Why are you asking?
You haven't said a word.
Y'all have been talking. Who would I talk to? They're all doing their own thing. Y'all, you're on your phone. What am I gonna say to you?
Staring at you.
I did make eye contact with you, Sky, and I just, I'm, yeah.
She's
so-
tired. I understand.
I'm not. I
There's no coffee mug today?
already drank my coffee. Hi, Charlotte. That email still did not have the
I noticed. I
first
was like,
problems on it.
it's always in the one.
You have at the top of that page, it says continued. There were other ones before that you haven't given me. There were the ones you did before the test. The other ones. Okay, I graded homework 7. I'm hoping that we're gonna get through enough today for you guys to do homework 8 by the end of this week. I won't be here on Thursday. So we are going to get through what we can today, and then I'm gonna have a video for you to watch for Thursday's class. I'll be at a math conference, having the time of my life.
Fun.
So I will, obviously, I'm recording class right now. I'll record our class now and post that on YouTube as soon as possible. But then I will record a video for class for Thursday. Y'all will watch that, fill in your note packets, whatever. We'll come back Tuesday. I'm expecting that you will be able to turn in your homework 8 by Tuesday. So homework 8 is going to be due on Tuesday. Everybody good? Homework 8 be due on Tuesday. Okay. So homework 8, written homework number 8, due on Tuesday. That's chapter 7, sections 1 through 4. And there's a worksheet in Blackboard also. So it's like 5 book problems and 5 problems from that worksheet. Okay. That's that. And I have the homework 7, so I'll get back to you later.
You know what the date is?
On Tuesday? Well, what is 12 plus 7? 19. Well, I'm good at modular arithmetic.
Okay, well, I'm all the way to discrete. I don't remember.
Adding. No, thank you. Okay, so that'll be due Tuesday, the 19th, your homework, written homework number 8. We'll get through that stuff, I think today, but certainly we'll be through it by Thursday. The next bit of stuff, chapter 5, is intense. So yeah. Okay. So I don't know if any of you remember what we were doing before we went on our spring break. Do you?
I had to watch the video. You're like, half the class is gone.
They were.
And then you're like, this is the easiest section that we're gonna do.
It was. So okay.
She said no right after that.
No. So we did one-to-one functions. We talked about what it means for a function to be one-to-one. We gave some examples of one-to-one functions. And then we talked about how you prove a function is one-to-one, which you pick 2 elements in the domain. So you have 2 darts and you're assuming that they land in the same spot. So assume that f of a equals f of b, so their images are the same, and show that they were actually the same dart. So the like scratch work here, you let a and b be in the domain. This first one, number 1, 6. I don't understand what's happening there. And then assume that f of a equals f of b. So fill in what that means. And then you get to a place where a equals b, and that's what you were supposed to be doing. So we're going to start with an example of that. Number 3 here, which we did the scratch work for on Thursday before we went on spring break, but that's been an eternity ago. So we're looking at this function that's going from the integers to the integers, and is defined by f of n equals n cubed. And we want to show that this is one-to-one. So we're going to let a and b be in our domain, and we're going to assume that f of a equals f of b. Function is, and take the cube root on both sides, and you are where we're supposed to be. So we're gonna write this proof now. So we're gonna let f from the integers to the integers be a function defined by f of n equals n cubed. We are going to let a and b be in z. Oh, some of you are doing this thing, Kaylee, you're doing this thing where you don't write proof before you start a proof. Somebody else, maybe Logan, you're saying suppose a lot. I want you to say assume or let. Yeah, instead. Those are like, well, that's not a small thing. You gotta start your proofs. That's it's not nitpicky, but it is, you don't want to suppose a thing, you're gonna assume it, you're gonna let it happen, yeah? Okay. All right, so we are gonna let A and B, unless you're like trying to do a contradiction proof, then you want to suppose, because you're doing it for the purpose of saying it doesn't work, right?
Right.
Yeah, okay. So we're gonna let A and B be integers here, and also in this case. F of A equals F of B. Maybe we can suppose here, because later on we'll say like, if this is true, then this is true. Yeah. No, whatever, it doesn't matter. Okay. So here, notice f of A equals F of B, which means that A cubed equals B cubed, which means that A equals B. And you're gonna say since A equals B, whenever, since the darts are the same, whenever they've landed in the same spot. So since A equals B, whenever F of A equals F of B, we have shown that F is 1-to-1.
Oh, we did have that proof then. And I missed it. You seem way too easy.
The 1-to-1 proofs are not that hard at all. Onto is a little bit harder, but we're getting to a point where we're trying to prove a bijection, which means it's injective and surjective, so it's 1-to-1 and onto. So it's like two proofs in one. So we're like, we're building to that point, right? These are not that bad. The functions themselves are not hard right now. This is a cubic function, like that's not hard. Unless we've forgotten everything from all of our other classes. Okay. So we have F here on number 4 is from Z cross Z to Z cross Z. So the input values here are ordered pairs that are integers, right? Yes, you with me? That the Z cross Z, this is the Cartesian product of the integers with the integers. So everything in Z cross Z looks like an ordered pair of integers. Yeah? Yes. Okay. So we're looking at F of Mn is equal to M plus N, comma, 2M plus N. So our input value is an ordered pair and our output value is an ordered pair. We want to figure out if this is 1-to-1. If so, we want to prove it. And if not, we want to find a counterexample. There's a lot happening there. What am I supposed to write? Scratch work in green? Yes, that's what that one looks like. So we'll continue to do that. All right. So for our scratch work here, which I noticed a lot of you aren't doing on your homework, and perhaps you should. For our scratch work here, maybe I should just give you the benefit of the doubt that you were doing it on a different piece of paper. I shouldn't. Okay. All right, I'm gonna use A, B, C, and D because I'm clever. We're gonna let A, B, C, and D be elements in Z cross Z.
Oh.
So we're picking 2 elements in the domain. We're gonna assume they're equal in the codomain, or that the image, they're equal under the function, yeah? That their images are the same. Are y'all with me or no? Are you? Feels like no. Their images are the same. The place that they landed was the same, is the same. Yes? Okay. So we are gonna assume f of AB equals f of CD. What do we want to show? We have no idea, Dr. Thomas.
Is it that?
We don't know.
Equals. Oh, yeah, AB equals CD.
Yeah, Why did you crap out in the middle of the ordered pair? AB equals C.
I thought I said D.
You did not. Yeah, we want to show that those two variables, those two things that were in the domain are actually the same thing. They're not two things. Right? Now it looks weird because it's like 4 things, because each one thing is 2 parts, but like it's fine, right? So we want to show that AB equals CD. What do we know from getting that f of AB equals f of CD? What do we know then? What's f of AB equal?
So good. Order pair,
Yeah, what order pair?
N plus N.
No,
A plus B.
Yes.
2A plus B,
yeah,
and the same for CD. You just plug it back into the function.
yes. You're just plugging in AB instead of MN,
Oh.
or CD instead of MN.
That's what I meant.
I
That's-
know.
meant that's the one you need to plug them in.
Yeah. Whitney, I saw a picture of you, speaking of, I don't know what it's speaking of, but I saw a picture of you from the like spring break trips. Where did you go?
To Irwin, Tennessee. It's not one of the ones, but it's really good.
Was Eunice on that trip?
Eunice.
Didn't Eunice go to Tennessee on spring break on a mission trip? Oh,
She went.
maybe New Orleans?
I forgot, she told me, I forgot. No.
Okay, where in Tennessee did
She's
you
like,
go?
I was in Tennessee, I didn't see her.
I was in Tennessee.
I searched all Tennessee.
It was Irwin.
Where is
Johnson-
Irwin?
Johnson City. It's
Okay,
like
yeah, I know where Johnson is.
Asheville.
Okay, cool. Did you have a good time?
I had a great
Good. How many people were on that trip?
time. 24, I think.
Oh, that's good. That's not that far from Knoxville, like an hour.
Oh, okay.
In the mountains more,
Uh,
up. I'm going to Knoxville this week.
okay.
That's where the math conference is. And that's where I'll be. Okay.
Fun.
I was in Tennessee on spring break too, but not in Irwin,
Where were you?
Nashville.
That's what's high.
That's where I'm from, so. Okay,
Knoxville's better.
so y'all, what does it mean for two ordered pairs to be equivalent? Like, how are we gonna show that AB equals CD? How do we show, what do we get from the fact that these two ordered pairs are equal? Yeah, eventually that's where we're going, right? We want to show that A equals C and B equals D, and then those ordered pairs would be equivalent. What do we have right now?
That A plus B is equal to C plus D,
And what else?
and 2A plus B is equal to C plus D.
Folks, this is a system of equations. And we're gonna solve it, sort of. If I subtract that top thing from the bottom thing, y'all are with me that I would get that A equals C? What? No, we're not. If I instead wrote this down here, that A plus B is C plus D, and I like subtract off this equation, you with me? Yes? Then I'm looking at A equals C.
Oh. Oh, okay, gotcha.
Great question. Well, A plus B equals C plus D, but A is C, so I'm looking at A plus B equals A plus D. Yeah,
Yeah.
so that means that B equals D.
Is it possible to use A plus C, like minus it out of?
Yeah, sure.
Wait, how did you get A plus B plus B plus C?
What? Wait, what? This step?
Yes.
Well, because I just proved that those were equal. That A and C are the same.
And C are the same. Oh, okay.
Okay, then, we did it, right? Y'all recognize that we're done? Mhm. We have that A is C and B is D, and for ordered pairs to be equivalent, the pieces are equivalent, and we just did that, yeah? Okay,
Oh, okay.
so we're gonna let F from Z cross Z into Z cross Z be a function defined by F of Mn is equal to M plus N. I don't remember what it's equal to, M plus N, comma, 2M plus N. We're gonna let X, not X, Y, I did A, B, and C, D. Let A, B, and C, D be elements in Z cross Z. Assume F of A, B equals F of C, D. We have A plus B, 2A plus B is equal to C plus D, 2C plus D. Then A plus B equals C plus D and 2A plus B equals 2C plus D.
A lot of other stuff.
Notice 2A plus B equals 2C plus D. We are going to subtract off A plus B equals, oh, sorry, get rid of that. A plus B equals C plus D, which gives us A equals C. I'm just copying scratch work now. Okay, so once we do all of that stuff, we have do subtraction, and you get that A equals C. And then since A equals C, we have that thing, the like first part of that, that A plus B is equal to C plus C, which we can replace the C with an A. And then we have B equals D. Then since A equals C and B equals D, we get that A, B is equal to C, D. Because since again, now we have shown that AB equals CD whenever F of AB equals F of CD. Thus, F is 1 to 1. What do you think?
A lot of letters.
Yeah, you said that. But what do you mean about the actual like math?
The math makes sense, it's
Yeah,
just
something.
confusing when there's a lot of letters. There's more than this.
That's fair, but you know, you can keep track of it, right? In theory. Daniel, you're stressing me out. It's the tapping.
Oh, sorry.
It's fine, but knock it off. Or tap quieter. I don't know. It's where I can't hear it or feel it. Yeah. Well, it's triggering my anxiety. So if you could knock it off, that'd be cool. Okay. So we are going to move now to doing onto or surjective. Is the Latin prefix. What is the word supposed to be? Maybe I shouldn't try to teach English for on. That's what the sur means. So a function is onto or surjective. What do you think that means? Think about it like this, that the domain maps onto the codomain. That it hits all of it. There's nothing left over, right? You've heard me saying all along, I don't know if you've noticed it, that this maps into this set, like R is mapping into R, right? Because I don't know that it's mapping onto the set, but I know it's mapping at least into it, yes? But mapping onto it means that there's nothing left. There's nothing on that dartboard that didn't get hit by something, okay? No, because the definition of function has every element in the domain has a thing it maps to, right? So the domain has nothing extra in it ever. And under any function. Cool. They're not equal.
Forget I said that.
Okay. Because everything in the domain could map to the same one thing in the range, right? Like the range could be just one thing. And that would still be a function. It wouldn't be one-to-one. But if it's both one-to-one and onto, they do match, and we're gonna get there.
Oh, it's supposed to be one-to-one.
It's not supposed to be, but there's a special kind of function that's both one-to-one and onto where the sets do like match. They have a one-to-one correspondent, and that's, we're gonna get there. We're not there yet. We're building.
So how can a function be onto and not?
I just said that if everything in the domain goes to one thing in the range. That's what I was just saying.
And that's the only thing.
No, well, if it's the range, yeah, but if it's a codomain, yes, if it is onto, good Lord almighty.
Because like there's only one possible output.
Potatoes. This is onto. This is not. Yeah, y'all haven't even let me write down the definition without all your questions. This is not onto. You with me?
Okay.
So like every.
This isn't a function.
Cause there's two, yeah, there's two coming out.
Good.
I know more functions.
Is this one-to-one?
No.
No,
No.
but if I maybe change these things. Is this one-to-one? Well, it's not a function, so no. Right, but what if I got rid of those?
Yes,
Yes.
that's one-to-one.
And it's on two.
Ah.
Here's a one-to-one function that's not on two.
Oh, so this like use up all the
okay.
inputs.
You always have to use up all of the inputs.
Okay.
If you use up all the outputs, it's on two.
Why didn't you say that?
I was trying to write down the freaking definition and you wouldn't let me. Basically, this is what I was gonna say, Charlotte, is this. If every element
It's not the part of it.
in Y has a pre-image in X. So it got hit by everything in Y got hit by something. Oh, well,
Should have said that earlier.
I should have. We will never know. So this is when your, the codomain actually equals the range. Yeah, remember we were talking earlier, I'm gonna scroll now. I know y'all are writing, but I'm gonna scroll kind of far. You ready?
Yep, you're right.
Ready. Okay. Not there. No, not there either. Here. Yeah, page 1. Look at this. Can there exist an element Y with no preimage in X? And the answer was yeah, because the range is a subset of the codomain, right? So the codomain is the big set we're mapping into. So you think about X squared, right? X squared going from R to R, reals to reals. You with me? X squared going from R to R, the reals to the reals. The domain is the real numbers. Everything on the X axis has a Y that it goes to, right? Yeah. The range, the codomain is also the real numbers. Yes, but we don't hit all of them. So the range is actually a subset of the real numbers. What numbers actually get hit by X squared? Well, the range, yeah, but what is it? What kind of numbers do you get out as an answer? Yes, there's real. Scott, what?
Rational.
Positive.
They're not integers, no, they're real numbers. They're positive, they're non-negative, real numbers. Because you can hit zeros still, right? X squared, you look at the, y'all have forgotten how to do domain and range? Domain, you go left to right, small to big. Range, you go bottom to top, small to big, yeah?
Mhm.
Domain for X squared is all real numbers, left to right, yeah. Range starts at 0, right, and goes to infinity, right? So if you designed your function, because that's what you're doing. If you made your function f from R to R, and it was X squared, this is not on 2 because the codomain doesn't equal the range. If instead you did this, that is on 2. Because you don't have anything extra in the range, in the codomain. Yeah, that the range equals the codomain.
So for it to be onto, does that mean you have to have an infinite range? It has to cover every single one?
No. Because that's not, right? I mean, I guess it's positively infinite, but no. The answer is no, and I don't know how to expand on that answer at all.
Oh, so but it can't have every. So it can have, like I guess in the other ones, they only have 3 dots. It's not infinite dots. It's just
Right.
3.
That, which is fine as long as all the dots get hit, right?
Mhm.
Okay, so we have, in this one, we want our code, if it's onto, we want our codomain to equal the range. So it's mapping onto this other set. So everything is getting hit. Think about like, if you're just, I don't know, you're gluing like an egg onto another egg. I have no idea where eggs or where my brain went, but it's fine. And I meant like a sticker egg. I didn't even mean like a real egg. Let's just talk about a piece of paper. How about we just use a piece of paper? Okay, so you have 2 pieces of paper. If one is going onto the other, think about that, like if they're the same size and you stack them up, every bit of the paper, of the top paper goes on top of every bit of the bottom paper, right? It covers it up, it's onto that thing, yeah? Right? Now, you can't have the paper, the input thing can't be bigger, because then you have domains that don't go anywhere, right? But it could be smaller. Yeah,
It wouldn't be on 2.
but it wouldn't be onto the other one, right?
It has to fit perfectly.
Onto the other one, yeah.
Makes sense.
Okay, I wish I had said that earlier. Okay, so symbolically, for all y and y, there exists an x and x. So every element in the range got mapped to by some element in the domain, right? Or in the codomain, every element in the codomain. There exists an element in the domain where it maps to that element in the codomain you were talking about. Well, shoot, look at me trying to do this example right now that we just did a second ago. It's really good. Oh, wow. Okay. So that looks kind of confusing, but for all y and y, there exists an x and x such that f of x equals y. That means any element that you pick, any spot on the dartboard that you pick, you can find a dart that hit it. A dart, at least one dart, could be many, right? We don't care, but at least one. Okay, so
No.
no what? Oh. No,
No.
no, why?
Because the codomain is not.
Make it 1-to-1. I mean onto, sorry. Don't make it 1-to-1. Yet.
Well, that would work.
But that's not what I was trying to ask. We have to restrict both the domain and the codomain, but whatever, we're not trying to do that yet. Well, how do I restrict the codomain to make this onto?
0 to.
Yeah, you say that like a question. We did it like 30 seconds ago. But yes. Right? Yes? Yeah. Because that would equal the range. I agree. Good. Awesome. I'm glad we're all on the same page. I'm ready to do the next one. Are you?
Yes.
Okay. Here we have this function from, that's supposed to be from, I got confused there. This function from ABCD to itself. All right, I'm drawing potatoes. I'm probably not gonna draw the potato part because I don't want to. Onto itself, to itself, to ABCD. Okay. F of A equals B. F of B equals B. Anybody see a problem?
But not
Do
They look like I guess.
we have a problem?
If
Yes.
we only have 4 in the domain until we were going to one of the 4 in the codomain, then one of them is going to be left out.
You're right. You're right. So far, it doesn't look like there's a problem, but Whitney can see into the future that we don't have any more elements. And the fact that these two went to the same one means that one of them is going to get left out. This hasn't broken the onto-ness yet, but it did break it being 1-to-1. Are you tracking that? Because those two different darts landed in the same spot. Yeah? Okay, so this breaks the 1-to-1-ness. And then, no, we're not just making a point. We're supposed to remember this stuff. F of C is A, F of D is D. Is this onto?
No.
No, because poor little C got left out. C has no pre-image. That's the problem. Nothing mapped to C, however you want to say that. All right, this is gonna be our hardest question so far today. Maybe. If we have F from R cross R, so that's an ordered pair to just the real number, so just a number. That's given by F of X equals X minus Y, is that onto? What does it mean to be onto?
Every pre-image the codomain equals the range for every.
Okay, so if the codomain equals the range, what does that mean? that we have to be able to get every real number as an answer, yeah? Right? Are there any real numbers that we can't get when we subtract two real numbers?
No.
No,
So
it
it's-
is.
yeah.
Mhm. Now I'm gonna do a little baby proof for you. Are you ready?
No, she's just saying that, just so we don't.
I said it's a baby proof. It's an introduction to what we will be proving later. Hold on, sorry, my husband needs me. My husband's doing a Facebook Marketplace exchange. He's letting me know he didn't get murdered, so we're good. Everybody's good. This is a problem when I do all the communicating, you know, and then he's got to actually do the interacting. Yes,
He does the dirty work.
he does. Yes. Have y'all seen the Nate Bargatze? Do y'all know Nate Bargatze? He's a comedian. He's fantastic, but he has this whole thing about Facebook Marketplace. Best case scenario, we get $5 for this thing. Worst case scenario, we all get murdered. Is it worth it? You know, it's pretty good. I suggest looking it up. Good luck spelling Bargatze. It's just like it sounds. Okay, so if we are picking some element in the codomain and I want to be able to find two elements now, I need to find n element, sorry, in the domain that map to R. Okay, so I need an XY ordered pair where, so this is an R cross R, where X minus Y equals R. So here's the thing, our R is arbitrary, right? So we're gonna come up with a particular way to get to that R, but because the R is arbitrary, that's an okay way to do the proof. Yeah? That was a lot of words I just said at you, but did you get it? No. There are a couple of ways to do this. Does it matter that we choose the same way? No. Does it matter it's gonna be a specific way that you say and that I say? No, because the R is arbitrary, it doesn't matter. You're just looking for an element in the domain that mapped to yours, right?
Right.
Okay, and since your element over here in the codomain is arbitrary, it doesn't matter. Okay. Can you come up with an ordered pair where you can subtract the two things and get R? You want me to give you an example? How about R and 0?
R is one of, oh, R is the.
R is a real number, right? If R is a real number, then I can use it. What if I use the ordered pair R0? What is f of R0? Well, it's R minus 0, that's R.
I didn't realize the other one was zero.
You could also use 2R and R, or 4R and 3R, 17R and 16R. Yep. Are you all right?
Yeah, that was weird.
What?
I don't know.
Okay.
I don't know what just happened. No idea. It's like some vertigo thing or stuff right there.
So again, the symbolically thing there, it says for all y in y, there exists an x in x such that f of x equals y. So for all y, you've chosen arbitrary y, right? We have arbitrary r here. There exists, so you gotta find an example, an element in your domain that maps to it. Either one of these will work.
kind of tricky, but it makes sense.
Yeah. So all of the onto proofs are gonna feel trippy because you're gonna do some stuff.
I don't know if I like that.
It's fine. It'll be fun. It'll be fun. I think they're fun. Okay, so symbolic statement again for all Y and Y. This is in your codomain. There exists an X in X that's in your domain, such that f of X equals Y. You're identifying that element's pre-image. You get what I'm saying? You're picking an element in the codomain and you're identifying the thing that got mapped to it, the dart that landed on that spot. Yeah? Okay, so you're gonna let Y be in Y. This is an element in your codomain. You're gonna construct an X in X. This is your domain. Gonna be careful with that. And it's specific to your Y. But your Y is arbitrary, so that's okay. And you're gonna show that f of X equals Y is true. Okay.
It was just blinking.
I don't know what's happening. Okay, so we're gonna let Y be in Y. Now, in this case, for this example, exercise 7.1, we're gonna prove that this function from R to R that's defined by X to the 5th plus 1 is onto. So we're gonna pick this Y in our codomain. That's not a pin. This is our codomain. And we're gonna find an X in X that maps to it. So we want to show that there exists an X in R, the domain, where f of X equals Y. Do y'all know how you did, how in like college algebra, you would find an inverse of a thing? You know, you like switched X and Y and solve for Y, right?
Yeah.
This is gonna look really kind of similar to that, but we're not gonna like switch X and Y.
Oh, no.
But here's what we're gonna do. We're gonna look at something like Y equals X to the 5th plus 1. What we're saying is that this is true, right? If f of X equals Y, this is the thing we're trying to show, right? If f of X equals Y, then this is true. You with me? Yeah?
Okay.
Well, I gotta get that X by itself. My second job number 2 here, bullet point number 2 was to construct my X in X. I want to find the X that I can plug in to get me Y back, right? So we're gonna isolate that X. So Y minus 1 is X to the 5th, and that's the 5th root of Y minus 1 equals X. So the way that we did that, in theory, if we plug that into our function, X to the 5th plus 1, everything's gonna cancel out, right? And we're gonna get that Y back.
Whoa.
So the question is this X that we found in our domain? If not, the function is not onto. Yeah,
Okay.
so is this in the real numbers? Well, yeah, taking the 5th root of a real number minus 1 is still gonna be real. Because it's 5th root, so the negatives doesn't matter, don't matter, right? Yeah. So then what you're gonna do is, so this is like, you know, this is the constructing part of this. So what we're gonna do now is show that f of X equals Y. So you're gonna do f of x is equal to f of the fifth root of y minus one, which is equal to, and you're plugging that into your function. So x to the fifth plus one. So this is the fifth root of y minus one to the fifth plus one. Are we tracking what I did there? I can't get it all on the screen at the same time, sorry. So we have constructed this x. Now that construction part won't go in your proof. That you're just leaving that off on the side. You're figuring out what that x is that you need. You're constructing that x, and then in your proof, you're gonna say, okay, suppose x, you are gonna use suppose there. Suppose x equals this thing. Well, look, when it does, we get this thing and it works and we're done. So you're gonna plug in that x to the function. So f of the fifth root of y minus one is gonna be the fifth root of y minus one to the fifth plus one. So the fifth root and the power, fifth power go away. So you're looking at y minus one plus one, and that's just y. Okay,
Oh, that's not bad.
so let's write a proof now.
We're done.
Well, yeah, we have more words in the proof itself, but yeah. Okay, so we're gonna let f from R to R be a function defined by f of x equals x to the fifth plus one. We're gonna let y be in R. This is the codomain. I'm trying to help you out here. And suppose x equals the fifth root of y minus one. Notice that x is in R also. Again, to be onto it means that every element in the range got mapped to by something in the domain. So we have this element in the range and we're finding the thing in the domain that maps to it. So suppose we have x is the fifth root of y minus one. Notice that x is a real number. Okay, now f of x equals f of the fifth root of y minus one, which is equal to the fifth root of y minus one to the fifth plus one. That is y minus one plus one, which is y. Here's your big finish. We have found x in R. Again, that is in your domain. Such that f of x equals y. So f is onto. What do we think? Is it okay? We're doing okay? Yes? No? Maybe? All righty. Now earlier. Good. Now earlier we said, if we changed the codomain on that one to 0 to infinity, it would be onto. Now, we're gonna prove it.
Yay.
All right, so we are going to again let y be an element in the codomain.
Oh. Why is it that this time? Why is it the 0 to infinity?
because that's the only way it can be on to.
So it's not y and element of y.
What?
Okay, never, ignore what I said.
I mean, the definitions are using X and Y as the domain and codomain, but they're not, they're different sets, you know? Those are just for the sets that they are. Okay, so we want to show that there exists a real number X such that f of X equals Y. Okay, so we're looking at Y equals X squared. This is the part where we're gonna construct our X. And hope it's in the domain. Okay, so if Y is X squared, how do I get that X by itself? I'm gonna take a square root, right?
Oh. Plug the F in.
Well, I don't have, that's two things. I need one thing
Oh,
that is in my domain. They are both in the domain, so you're just gonna pick one of them.
can you just
Okay.
pick- Yeah, I don't like negative. Could you pick the negative? Maybe it's the same?
Yep. So since you're doing a there exists statement, right? You have a for all Y, there exists an X, so there are actually two, but we don't care about that. We just want to show that there is at least one, right? So we're gonna pick one and show it. The pick positive one, pick the negative one. I don't care what you do. I mean, as long as it's one of those things. All right, so we are gonna let F from R to, oh, I didn't actually do any more, whatever, it's fine. Let F from the reals to the non-negative reals be a function defined by f of X equals X squared. We are gonna let Y be an element in the non-negative real numbers. Again, this is your codomain. And suppose X is equal to the square root of Y. I chose positive one. Now, f of X is equal to f of the square root of Y, which is equal to the square root of Y squared, which is equal to Y. Oh, I should say up here, notice X is an element in the real numbers, which is our domain. So we have found an X in the real numbers such that f of X equals Y. So F is on 2. Questions, comments, anything you got? We're good?
We'll see when we get to it.
The book problems, you don't have to do one-to-one or on-to proofs. Those are in the worksheet. The book problems are more like, do you understand the definitions, stuff like that. You get to decide if the thing given to you is one-to-one or on-to, but you don't have to like do a proof, except for on the worksheet, then you do. Lots. But there are 10 there, so you know, you could feel free to do them all. Okay. If I was, you know, the type of professor who would put the ones that you didn't have to do on your exam, which I am. So I sure am. Okay, so that's number 2. Do you have any questions about number 2? Does the idea of an on-to proof make sense to you? All right, let's do another one then. Let's do this one and then we're going to move on to bijections. All right, so we have this function from z cross z into z. So take an ordered pair of integers, get back an integer. The ordered pair mn, you do 2m minus n to get to the answer. Okay, so we are going to let y be an element in the integers. This is our codomain. And we want to find there exists a, I don't know, we're gonna call it AB in Z cross Z, where 2A minus B equals Y. So what we know right now is that Y is an integer. What we're trying to find is an ordered pair of integers where 2 times 1 minus 1 is Y. Not 2 times 1, but 2 times one of them, whatever. We want to find an ordered pair A, B, where A and B are both integers, and 2A minus B gives us Y, which is also an integer. It doesn't have to be. Which one you want to make a 0? Yeah, I don't see how we can do that. If A is 0, what does B have to be? Negative Y. What about YY? What's 2Y minus Y? It's just Y. Yeah. Why is that? Well, you have 2 oranges and someone takes away an orange. How many oranges do you have left?
2 in a broken hand.
Okay.
Count how many times you said Y in this problem.
I know. Okay. Y'all want me to use 0 and negative Y, or you want me to use YY? YY. Okay, so we're gonna let f from Z cross Z into / onto Z be a function defined by f of mn equals 2m minus n. We are going to let y be an element in Z, which is our codomain. And suppose mn is equal to yy, then f of mn equals f of yy, which is 2y minus y, which is y. So, oh, I didn't do this here again. Notice, sorry, back up. Notice y is an element in z cross z, which is our domain. There's a reason I keep doing this, y'all. Because if the thing you get's not always in your domain, that's a problem. But y is always in the domain because y is an integer, so y will always be in z cross z. Yeah. Okay. This gets weirder when you're doing integers with division, right? Which is why it wouldn't work to make like b 0 here, because I'd have to divide y by 2 or something. And like I can't do that because I don't know that the y is even, right? So being careful here, especially if you're working with the integers, because subtraction of integers gives you integers, but division that's not true. So all right, so we have then found an mn in z cross z, or we have found an element in the domain that whose image is y. Let's go with that. Therefore, f is onto. Questions, anything? How are we feeling about this? Fine, good. All right, we're gonna skip that one. We're gonna go to this one.
Oh.
Yes, I can.
Number 4, 1, 2.
No, it's different. You want me to figure this out right now? A, B, C, A. I'm writing with an Apple pencil on my paper, like I'm gonna be able to look back at that. Y'all, shoot, no, I can't do, eek.
It's fine.
I think,
This is the question that said.
Different from number 4 from page 6.
the function may not be different, but we were proving 1-to-1 on that one, weren't we?
Yeah. Improving that it was one.
No.
Oh, I see.
1-to-1 is that if they're in the same spot in the codomain, they are actually the same thing in the domain, right? But that doesn't mean that everything got used up, right? If they were the same, we wouldn't be doing this in 2 different things, right? Again, let me draw you a picture. This is 1-to-1, but not on 2. Okay. A bijection is both 1-to-1 and on 2. This is called a 1-to-1 correspondence. Agree or disagree that makes it sound like they're not on 2.
What? I agree.
So I don't ever use those words, like on a test, I'm not gonna write 1-to-1 correspondence. I'm gonna call it a bijection, but it means it's 1-to-1 both ways. Every input has one output and every output came from one input. So a 1-to-1 correspondence is, Whitney, what you were hinting at earlier, where everything in the domain hit something and only one thing, and everything in the range everything in the codomain got hit by something, but only one, only one thing. Okay. Oh, I don't have a definition written here. Let's do that, where every element in Y has a unique preimage.
Is it very?
Mhm.
It's an ongoing joke.
Well, I'm not part of that joke, so. This every element part, the every element in Y, that's the onto part, right? That every element in Y gets hit. That's the onto part. The unique part is the one-to-one. So every element in Y has a unique preimage in X. It has a one-to-one correspondence, every one arrow from and to everything. Okay. So how are you going to do a proof that something is a bijection or a one-to-one correspondence? It's not really cases, but it's like two mini proofs. Yeah. You're going to prove first that it's one-to-one and then second that it's onto, or what the other order. I don't care. But you have to prove both things to be true, that it's both one-to-one and onto. So let's do that now. All right, so to do the bijection, we need to do a proof that there's one-to-one, and we need to do a proof that it is onto. These are involved because you got to do two proofs, yeah? Inside the same proof. So to prove that it is one-to-one, how do we do that again? We have two darts, they landed in the same spot. We got to show that they're the same dart, right? So we're gonna let A and B be elements in your domain. Assume f of A equals f of B. Show A equals B. If f of A equals f of B, what do we have in this particular example? That gives us that A equals B eventually, so we're good to go. So it is one-to-one. Okay, now how do we prove that it is onto? Where do we start for an onto proof? So we want to show that there exists an element in the codomain, which is also the real numbers. I mean, in the domain, which is also the real numbers, that where f of x equals y. This is the construction part. You're not going to do this in your proof. 2x plus 1 is y. That means y minus 1 is 2x. That means y minus 1 over 2 is x. The question is that a real number? Yeah. So then we have done it. We found the element and we're good to go. So we're going to let f from R to R be a function defined by f of x equals 2x plus 1. We will show f is a bijection. Okay, so we're first going to let A and B be in the real numbers and suppose f of A equals f of B. Well, then two A plus one equals two B plus one, and it follows that A equals B. So since A equals B, whenever f of A equals f of B, f is 1 to 1. My hand's starting to hurt now. Y'all's? No? Hmm. All right, and then we're gonna do the onto part. We are going to let Y be an element in R. Remember, that is your codomain. And suppose ooh, X equals Y minus 1 over 2. Notice X is a real number, which is our domain. Observe f of X equals f of Y minus 1 over 2, which is equal to, I have no idea what the function is anymore, 2 times Y minus 1 over 2 plus 1, which is Y minus 1 plus 1, which is just Y. We have found X in R such that f of X equals Y. So, so F is onto. Now, F is both 1 to 1 and onto. So it is a bijection box. Oh man, tomorrow is an early release day again. I think we just had one. It's okay. It's more time to hang out. Y'all don't have to be here on Thursday, so that basically is one, right? You do have to do work at some point, but it doesn't have to be Thursday. Okay, so are we done with that proof? Do y'all understand? Bijection proof just means combine the two proofs into one proof. Yeah? All right, so 1 to 1 onto proofs. Here's a little summary. To show F is 1 to 1, you're gonna pick A, B, and X, and suppose f of A equals f of B, show A equals B. To show something is not 1 to 1, you want to find A, B, and X, where f of A equals f of B, and, or but, A doesn't equal B. But they were actually two different darts. For an onto proof, you were going to pick Y and Y, your codomain, and find, that means construct, an X in your domain such that f of x equals y. To show f is not on 2, you are going to show that there exists a y in y with no pre-image in x. All right, I'm over my time. Y'all have a great day. I will see you next Tuesday. Remember, your homework number 8 is gonna be due next Tuesday, the 19th, 1 week from today. Cool? And I'll have a video that I will post for you for class for Thursday. I'll probably make it in the morning while my kid's in school for 2 hours. Yep,